So here we have 3.5 times 10 to the 7th newtons is equal to 1.5 times 10 to the 4th, right? Kilograms per second times u. Now again, I put positive in here because they just want speed, right? So my u, which is the exhaust speed, comes out to 2,333 meters per second, or u is equal to, this should be kilometers, by the way, not kilograms. 2.33 kilometers per second. The burn time, right? So the mass of fuel, right, is 73% of the total original mass, right? So 73% of MO, right? Which is 0.73 times 3 times 10 to the 6 kilograms, right? And that, if you do your calculation, it should be 2.19 times 10 to the 6 kilograms of fuel, right? Well, if we have this much fuel, how much can we burn this, right? So if we multiply this or divide this by the burn rate, we'll get the seconds, right? So therefore, 2.19 times 10 to the 6 kilograms, divide that by 1.5 times 10 to the 4th kilograms per second, gives us 146 seconds. So they could only burn for 146 seconds. After 146 seconds, no more fuel. All right, what's the final speed? My VF is equal to, well, maybe I should use different color, but VI plus U ln of initial mass over final mass, right? So, what is the initial mass? Well, we know initial mass is equal to 3 times 10 to the 6 kilograms. Right? The final mass is this minus the fuel, just the payload, really, right? So mass final is equal to 3 times 10 to the 6 kilograms minus 2.19 times 10 to the 6 kilograms. So the mass final comes out to 0.81 times 10 to the 6 kilograms. All right? So if you plug and chug, right, my VF is equal to initial velocity is 0 because hopefully the rocket is at rest when the astronauts are getting in, plus U, which we calculated to be 2.33 kilometers per second, right, times ln of, right, 3 times 10 to the 6th kilograms over 0.81 times 10 to the 6 kilograms. So if you work that out in your calculator, your final velocity should come out to 3.05 kilometers per second. That's sick, right? That's pretty fast. All right. All right. Moving on. Let's do the mass distribution now. All right, center of mass for a continuous mass distribution. For point particles, we did this, right? X sub Cm is equal to m1 x1 plus m2 x2 plus blah 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 over total mass m1 plus m2 plus etc. So it's a summation of mn xn over total mass, right? Well, for continuous mass distribution, right? If you were to think about cutting a little tiny pieces off on every one of these little, right? This whole bar that is uniform density, right? So this little tiny dm, right, of this dx right here, right, dx, and this is dm, right? So you could literally split this up at infinitesimally small, right? So dx is differential space, right? Okay. And dm, right? Dm, there are infinite number of dm's, I guess, from 0 to L, right? So if we split them up in that infinitesimally slivers, okay, where the dx approaches 0, right? Then we can actually integrate this thing. All right. So the dm and then x. So x is actually from origin to where that dm is located, right? That's my x, location of my dm's, right? So if we add up all these little slivers of dm and multiply that by where the dm is, which is the position x, right? Then divide that by the total mass, where we take the dm approaches 0, right? It just like shrinks it down to 0. We're just integrating it. So x sub cm is equal to now, right? Integral of x dm over the total mass m, right? So integration. So let's see if we can apply this. Let's see if we can apply this. All right. There are two versions on this problem, right? A, uniform density, kilograms per meter. So this is linear density, right? I think we talked about linear density being lambda. Area density is, sigma, and then volume density is rho. Okay, so linear density is mass divided by length, and it should be constant because it's uniform, right? Now there's a non-uniform density where, like, I guess you could have different materials made with, like, fused together, right? Have different densities. Then lambda of x, depending on where the location is like beta x, or beta is some constant that we know. And depending on where the position of that x is, you would have different densities. Okay? So we're going to approach one with just uniform density first, without even like knowing calculus or physics, if I were to ask you to balance this bar that's uniform density, what would you do it? We all know instinctively, oh, we'll stick my finger at the halfway point, it should balance, right? Which is L over 2. Well, we're going to prove that using calculus. I mean, we can, right? So first of all, if we were to cut out little tiny dm here, this dm is located, right, x distance away from the 0, right? This is x distance away, right? So if we were to prove this by using x sub cm is equal to integral from 0 to L dmx over the total mass m. You know this is constant, right? This has to be constant right here because total mass doesn't really change, okay? So how do we actually fix this little dm right here? Well, you know that dm over dx is linear density of that little tiny little piece, which is represented with lambda. That lambda should be same with the total mass over total length, which is also constant, right? So if we were to look at these two together, so dm over dx should equal to total mass over L. Well, let's solve for what dm is. Then dm is equal to, right, m over L dx. So we shall substitute this into my dm. Okay, so this is very important, right? So always replace dm with dx, right, using lambda or sigma or, right, or rho, depending on what you're working with. Okay? All right. So if we do that, if we substitute that in, x sub cm is equal to integral of 0 to L, right, m over L, right, times x times dx over m. Okay? So notice how the total masses cancel out. And the length itself here is also constant, right? The length is not going to automatically change on us, right? So 1 over L, integral of 0 to L, x dx. We know how to integrate that, right? So this is 1 over L, right? X squared over 2, evaluated from 0 to L, right? And that is equal to 1 over L times x squared, replace that with L, I get L squared over 2 minus 0. So that comes out to L over 2 minus 0, which is L over 2. So my x sub cm, which we already predicted, comes out to L over 2. Well, that was easy. So we know it works. We know this works. So let's take a look at something more complex. Okay, let's take a look at some more complex. Let's say it is not a uniform. Let's say it's not a uniform density, where my lambda is actually is a function of position x, and it is beta x. Okay? We're not going to really change the procedure of this. What we have to do is we have to basically do the exact same systematic thing, right? So again, if we were to cut out this 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 little dm here at position x, right, from 0, right, we still say the x sub cm is equal to integral of 0 to L dm x over the capital M, right? So we know that dm over dx is equal to lambda, but they also gave us lambda as beta x. So my dm is equal to beta x dx. So when I substitute this into my dm, right? So again, x sub cm now is equal to the integral of 0 to L beta x dx times x over m. All right? So we know that this is constant. We know this is constant, so we can factor them out. So we got beta over m, right? And integrate that from 0 to L x squared dx. Therefore, we know how to integrate that, right? So beta over m. This is x cubed over 3 evaluated from 0 to L. So beta over m times x cubed over 3 minus 0. So my x sub cm comes out to, right, beta L cubed over 3m. Okay. So that's not that bad. Okay, so the procedure is still the same. You know, replace the dm with, you know, dx. Okay. All right. Now let's take a look at something more different. Think of the one-dimensional line in the previous example and bending it into half circle. Now you know you're going to have to go with polar coordinate system here, right? So if I were to cut a little tiny piece here, right? This dm, right, is located. I need a ruler. Darn it, ruler. I'll give you half of my kingdom for a ruler. Can't find it. All right. Oh, there it is. So here, you don't laugh. All right. So here, this location of my dm is actually r distance away from the origin. And we all know that r can be represented in a component of x and y, right? So this is x, right? X is equal to r cosine theta, which is theta right here, and y is equal to r sine theta, right? All right. And this, instead of delta x, it is ds, right? So this dm, right, sits on a differential arc length, right? ds, right? Which is that little tiny sliver that we cut out for that, right? dm. And since, right, theta is equal to s over r, right? R is going to be constant because R doesn't change. The radius doesn't change, right? So if you take a derivative on both sides, right, d theta is equal to ds over r. So what's my ds? My ds is equal to r d theta, right? So we're going to have to use polar coordinate system here, okay? Now you know as far as the x is concerned, your center of mass is going to be symmetrical along the y-axis, right? So you know instinctively your center of mass has to lie along the y-axis somewhere. So we're not going to even do the x because most likely the x is going to come out to be 0 anyway. I mean, if you want to do it, you can. You could still do it, all right? So we must use polar coordinate system. Okay? So dm over ds is equal to total mass over total length L. So dm, again, is equal to m over the length L ds. But what is this length L? L is semicircular, so it's instead of 2 pi r, it's pi r, right? So dm is equal to m over pi r. ds, we already said it was r d theta, right? So r d theta is what we have for dm. Okay, so notice how the r's cancel out. So my dm is equal to m over pi d theta. This is only true for this problem. Okay, so you cannot use this as a general equation. So, oh, every time I see a dm, I should be using this. No. Okay, so make sure you understand that. So we shall substitute this for my dm in my general equation. So we already established that x sub cm is equal to 0, right? We know the symmetry of this, so we're going to actually just know that. And if you want to give it a shot, you can, because x sub cm is still going to be this x dm, right, over the total m, and you should be able to still do the exact same thing as this and put it in here, and you should be able to get that 0. Okay? However, let's do the y. Okay, let's do the y. Integral of, right, y dm over m. I'm not going to put the parameters in there yet because we're not going to actually use this dm yet, right? So it's going to eventually going to be from 0 all the way to 180 degrees, or if you're going to use in radiant mode, which you should, 0 to pi will be the eventual parameters, but hold that thought. So here, when we replace this dm, okay, so I'm going to factor out this m out, I guess, so 1 over m integral of, we know the y is r sine theta, right? So we substitute that in there. So r sine theta times dm, which is m over pi d theta. So we know radius is going to stay constant. We know the mass is going to, right, stay constant. Pi is constant. So we're going to say r m over m pi integral of sine theta d theta from 0 to pi. As you can see, the masses cancel out nicely. And you get r over pi, right? Integral of 0 to pi sine theta d theta. We know how to take integral of sine, right? It's negative cosine. Therefore, r over pi times negative cosine theta, evaluated from 0 to pi. Therefore, let's take that negative sign out. Negative r over pi. Right? So what is cosine of pi minus cosine of 0? What's cosine of pi? This is negative 1. Cosine of 0 minus cosine of 0 is just 1. So you get negative 2 here, right? So negative r over pi times negative 2 gives me 2r over pi. And it becomes positive, right? Positive 2r over pi. So my y sub cm is equal to positive 2r over pi. Well, what is 2r over pi? Well, that's like almost 2/3 of r, right? So if you were to find what that 2 over pi is, that's 0.637 r is what the center of mass should be, right? So if this is r, 2/3 r, it's going to be somewhere around here, around there, like 0.6. Right? So this is like 0.6, oops, 0.637 r. Okay? So 0, comma 0.637 r. So this center of mass is outside of the system. Okay? And that's how we do it. All right? All right. Last one. This is 90 degrees here. Don't rotate this thing. I know some students actually rotate this thing from 0 to, like, pi over 2. But don't do it that way. Work with what you have and work with symmetry. Because if you have to rotate this thing to like this, then your x will not have symmetry, and you would have to calculate for both x and y, and it's going to be somewhere here instead of right at the center on the y-axis. All right, so don't rotate it. So if this is 90 degrees here, and this right here is actually then 45 degrees, this is 45 and this is 45. Okay, so this is like pi over 4, right? To, right, 3 pi over 4, right? All right. So again, if you were to do the dm here, right? And then I'm going to help you just set it up, so you should be able to do this to check your understanding. Okay, again, this is the R, right? This is the R. Again, the X I'm not going to worry about because it's the symmetry. We're going to just talk about the Y, right? So the Y is equal to R sine theta. Okay, X R cosine theta, but we're not going to worry about the X because X is got symmetry. Okay. So again, X of Cm, which is equal to, right? Right. Let's do the Y. Okay. Again, the density, right? dm over ds is equal to m over L. dm is equal to m over L ds. But the L is actually half of pi r, right? So L is equal to 1/4 of 2 pi r, which is pi r over 2, right? And ds is equal to r d theta. So this is good to know, right? So my dm is equal to, right, m over pi r over 2, right, r d theta. So my dm is equal to, again, the r's will cancel out, it'll be 2m over pi d theta. So this is important. So my y sub cm is equal to, right, I'm going to factor out the m, so 1 over m integral of y, which is r sine theta, times dm, which is 2m over pi d theta. So if we factor out all the constants, right, and it's going to go from pi over 4 to 3 pi over 4. Okay? And if you want to put it in degrees and put these in degree mode, you could go from like 45 to 135. And that's also fine too. Right? So here we got 2m r over m pi, right? Integrate that from sine theta, right? d theta, pi over 4 to 3 pi over 4. 2 misters, no, just kidding. 2r over pi. Right? Integrate that, and then we'll get negative cosine theta from 3 pi over 4 to pi over 4, right? So negative 2r over pi times, right, cosine of 3 pi over 4 minus cosine of pi over 4. This is negative 0.707 minus this is positive 0.707. Therefore, this comes out to, right? I'm going to just give you the answer. 0.9r is my y sub cm. So if you want to write down r sub cm is equal to, right, 0 I hat plus 0.9 r j hat would be the proper answer for that. All right. Any questions? Okay, then. Wow, we made it. 8:35. Sorry for the delay this morning, guys. I guess technical issues do happen to teachers too. Okay. If there are no questions, then have a wonderful day. I'll stop my lecture here. All right.